MPLS-TP Multiprotocol Label Switching, Transport Profile, is a simplified version of MPLS designed specifically for the transport layer of telecommunications networks. It was co-developed by the IETF and ITUT to bridge the gap between pure IP/MPLS, which is complex and dynamic, and the traditional reliability of optical transport, like SONET/SDH. Think of MPLS-TP as MPLS for transport engineers. It removes the complex IP-based features that transport networks don't need while adding the heavy-duty monitoring and protection tools they require. Why was MPLS-TP created? Standard IP/MPLS relies heavily on a control plane, IP routing protocols like OSPF and LDP. If those protocols fail, the whole network can lose its way. Transport networks, which carry the backbone traffic for entire countries, require deterministic behavior. A path must be fixed and stay fixed unless a human or a management system changes it. MPLS-TP was created to provide this SDH-like predictability over a packet-switched infrastructure. Key differences: MPLS versus MPLS-TP Features. Standard IP/MPLS MPLS-TP Dynamic, IP-based control plane. Static/centralized, NMS controlled, OSPF/LDP/RSVP, IP dependency required for routing and signaling not required, can run without IP, paths can change dynamically. Strictly deterministic and bidirectional. OAM limited/optional. Comprehensive and mandatory, monitoring, protection. Switching, 50 milliseconds. Recovery rerouting, seconds to ms, guaranteed. Key features of MPLS-TP: astatic provisioning. Unlike standard MPLS where routers talk to each other to find paths, MPLS-TP paths are usually set by a network management system, NMS. This ensures that the traffic always follows the exact fiber path intended by the engineer, which is critical for capacity planning. Bidirectional LSBs. In standard MPLS, the path from A to B is separate from B to A, unidirectional. In MPLS-TP, paths are co-routed bidirectionally. This makes troubleshooting much easier because the transmit and receive paths are identical. See Advanced OAM, Operations, Administration, and Maintenance. This is the heart of MPLS-TP. It includes built-in tools to monitor the health of the connection continuously, continuity check, CC like a heartbeat, sending small packets to ensure the path is still alive. Remote defect indication, RDI tells the other end that a failure has occurred. Performance monitoring, measuring delay and packet loss in real time. D-carrier grade protection, APS, MPLS-TP uses automatic protection switching, APS. If a fiber is cut, the hardware detects the loss of the heartbeat, OAM, and instantly flips the traffic to a pre-configured backup path in less than 50 milliseconds. How MPLS-TP fits in the network. In a telecom stack, MPLS-TP usually sits between the high-speed optical layer, OTN/DWDM, and the service layer, Ethernet/IP. One OTN/DWDM provides the raw light/bandwidth. 2 MPLS-TP organizes that bandwidth into reliable, monitored logical pipes. 3 services carries 4G/5G mobile backhaul, business Ethernet, or wholesale traffic inside those pipes. The architecture of MPLS-TP, multi-protocol label switching, transport profile, is structured to provide a connection-oriented transport layer that mimics the behavior of traditional transport technologies, like SDH, while using the efficiency of packet switching. Its architecture is defined by 3 primary planes: the data plane, the management plane, and the control plane. The data plane, forwarding. The data plane is responsible for the actual movement of packets. It is designed to be IP independent, meaning it can forward traffic without needing an IP address in the header. Encapsulation, it uses the standard MPLS 32-bit shim header. LSP structure, unlike standard MPLS, the paths, LSBs, in the data plane are bidirectional and co-routed. This means the forward and return paths follow the exact same physical routers and links. Encapsulation layers, * section layer, the physical link between 2 adjacent nodes. LSP layer, the end-to-end path through the network. PW, pseudo-wire, layer, the specific service, like an Ethernet wire, carried inside the LSP. The management plane, NMS, in MPLS-TP, the management plane is the brain. Because transport networks require high predictability, paths are often not created by the routers themselves but by a centralized system. Static provisioning, a network management system, NMS, defines the labels and paths for every router in the chain. Inventory and configuration, it handles the manual or semi-automated setup of LSPs and pseudo-wires. Fault management, it receives alarms from the OAM mechanisms to notify engineers of fiber cuts or hardware failures. The control plane, optional, this is a major architectural difference from standard IP/MPLS. Optionality, in MPLS-TP, a dynamic control plane is optional. If used, It is typically GMPLS, generalized MPLS. Function, it can be used to automate the setup of paths or to provide restoration, finding a new path if both the primary and backup paths fail. Independence, the data plane can continue to forward traffic and perform protection switching even if the control plane fails entirely. OAM architecture, monitoring, OAM, operations, administration, and maintenance, is integrated into the architecture to ensure carrier-grade reliability. It operates using a special label called the GAL, Generic Associated Channel Label. Fault detection, uses continuity check, CC, messages to monitor the path every few milliseconds. 6 Localization, uses loopback and link trace to find exactly which fiber or port is broken. Performance, architecture allows for measuring one-way and two-way delay, latency, and packet loss. Survival/protection architecture. The architecture is built for high availability. It uses a 1:1 or 1+1 protection scheme, working path, the primary path for data. Protect path, a pre-provisioned standby path. APS, automatic protection switching, the architectural logic that triggers a switch to the protect path within 50 milliseconds if the OAM detects a failure in the working path. Summary of the layered architecture: layer responsibility, service layer, the client traffic, Ethernet, TDM, etc. PW layer encapsulates client traffic into a pseudo wire. LSP layer tunnels the PW across the transport network. Section layer manages the physical link transmission, example over OTN or Ethernet. MPLS-TP features. MPLS-TP provides the best of both worlds, the efficiency of packets, like MPLS, it uses labels and statistical multiplexing to save bandwidth. The reliability of transport, like SDH/SONET, it is predictable, easy to manage, and recovers instantly from failures. MPLS-TP, transport profile, was engineered to bring the deterministic, always-on reliability of traditional optical transport to the world of packet switching. Its features are specifically designed to eliminate the unpredictability of standard IP routing. One control plane, static and centralized. The most defining feature of MPLS-TP is its departure from the dynamic, often unpredictable control planes of standard MPLS. NMS-driven, in a transport environment, engineers want to know exactly which fiber a circuit is using. MPLS-TP allows for static provisioning via a network management system, NMS. Labels are manually or semi-automatically assigned. IP-free operation, standard MPLS requires an IP control plane, OSPF, LDP, to function. MPLS-TP can operate without any IP addresses in the data plane, reducing the attack surface and complexity of the network. Predictable routing, paths do not reconverge or shift automatically based on a routing protocol's algorithm. They only change if explicitly commanded by the management layer or a protection trigger. 2 OAM, operations, administration, and maintenance. In a telecom backbone, you cannot manage what you cannot measure. MPLS-TP features a robust, hardware-embedded OAM toolset, based on ITU-TY.1731. Continuity check, CC proactive heartbeat packets sent at high frequencies, example every 3.3 milliseconds, to ensure the path is up. Fault localization, tools like ACE, alarm indication signal, and LDI, link down indication, help suppress alarm storms by identifying exactly where a failure occurred. Performance monitoring, PM, it measures frame loss, frame delay, and delay variation, jitter, with microsecond precision, ensuring service level agreements, SLAs, are met. 3 Protection, 50 milliseconds survivability. MPLS-TP provides carrier-grade protection, mirroring the reliability of old SONET/SDH rings. 9 Linear protection, 1:1 and 1+1. A working path is paired with a protection path 10. If the OAM heartbeat fails, the traffic switches to the backup. APS, automatic protection switching, the hardware triggers the switch in under 50 milliseconds. Ring protection, supports G.8032, ERPS, or similar mechanisms for sub-50 ms recovery in ring topologies, ensuring that even a double fiber cut in a large network can be mitigated. 4 Deterministic behavior. Deterministic means that for any given input, the output and the time it takes to get there are always the same. Bidirectional co-routed paths, unlike standard MPLS where the go and return paths can be different, MPLS-TP ensures both directions follow the same physical route. This makes latency symmetrical and troubleshooting intuitive. Fixed resource allocation, bandwidth is often hard reserved. A 1 Gbps MPLS-TP tunnel will always have 1 Gbps available, regardless of how much best effort internet traffic is flooding the rest of the network. No jitter, by avoiding dynamic rerouting and using strict priority queuing, MPLS-TP provides the stable timing required for synchronized services like mobile towers. 5 Multi-service support, the universal carrier, MPLS-TP uses pseudo wires, PW, to carry different types of traffic over a single unified backbone. 11 Legacy support, it can carry TDM, E1/T1, and ATM traffic, allowing older telecom equipment to run over a modern packet network, circuit emulation. Ethernet private lines, E-line/ELAN. It provides transparent wires for business customers. 5G/mobile backhaul, it carries highly sensitive timing and data traffic for mobile base stations simultaneously. Summary table. Feature purpose: transport benefit control plane static/manual setup, total path predictability and security. OAM proactive monitoring, instant fault detection and slaw proof. Protection APS, 50 milliseconds, same reliability as fiber/SDH. Deterministic co-routed path, symmetrical latency and stable timing. Multi-service pseudo wires, PW, one network for voice, data, and legacy. Application of MPLS-TP. MPLS-TP, transport profile, has carved out a specific niche in the telecommunications ecosystem. While standard IP/MPLS is the king of the public internet and flexible routing, MPLS-TP is the workhorse for infrastructure that requires absolute stability, high availability, and 50 milliseconds protection. Here is where MPLS-TP is most commonly applied: 1. Carrier transport networks, aggregation and core. In the hierarchy of a carrier network, MPLS-TP acts as the aggregation layer that sits between the access network, user side, and the optical core, DWDM. The role: carriers use MPLS-TP to aggregate thousands of smaller customer connections into high-speed pipes, 10G, 100G. Why MPLS-TP? Unlike standard MPLS, which might shift paths dynamically and cause a brief hiccup in traffic, MPLS-TP provides deterministic paths. A carrier can guarantee a customer that their data will follow a specific physical fiber path through the city, which is essential for capacity planning and predictable latency. 2. Mobile backhaul, 4G LTE and 5G, mobile networks are perhaps the largest users of MPLS-TP today. The role: it connects the cell site, base station, to the mobile core, EPC/5GC. Precision timing: 5G towers require nanosecond level synchronization to handle handovers as people move between cells. MPLS-TP supports IEEE 1588v2, PTP, and synchronous Ethernet, SYNC, with high stability because it lacks the jitter caused by dynamic routing protocols. Symmetrical latency: because MPLS-TP uses co-routed bidirectional paths, the delay to and from the cell tower is identical. This is critical for the timing algorithms used in mobile coordination. 3. Enterprise VPNs with strict SLAs for high-value clients such as banks, stock exchanges, and hospitals. Standard best effort internet or even standard MPLS is sometimes not enough. The role: providing premium L2 VPN, E-line or ELAN, services. Guaranteed performance: because MPLS-TP allows for hard bandwidth reservation, a bank can have a 1 Gbps virtual wire between offices that is physically isolated from other traffic. Slaw proof: the deep OAM, operations, administration, and maintenance capabilities of MPLS-TP provide the carrier with real-time reports on packet loss and latency, which they use to prove they are meeting the 99.999% uptime requirements of the Service Level Agreement, SLA. 4. Multi-service transport over DWDM. Telecom providers often have to carry a messy mix of old and new technologies. MPLS-TP is the perfect packet optical integrator. The role: encapsulating multiple services into a single DWDM wavelength. Circuit emulation: CES. Many utilities, power companies, and transport systems, railways, still use legacy TDM, E1/T1, or ATM for signaling. MPLS-TP uses pseudo wires to wrap these old circuits and carry them over a modern fiber backbone without breaking the original timing. Efficiency: instead of dedicating a whole DWDM wavelength to a low-speed service, MPLS-TP multiplexes dozens of different services, Ethernet, voice, video, into one high-speed OTN container. 5. Critical infrastructure: power, rail, oil and gas. Industrial networks require fail-safe operations where a network reconvergence time of 2 seconds, typical for OSPF/IP, could cause a power grid to trip. The role: managing the communications for power substations or railway signaling. Reliability: the 50 milliseconds automatic protection switching, APS, of MPLS-TP is non-negotiable here. Even if a fiber optic cable is cut by a backhoe, the protection logic is so fast that the industrial sensors never even see the interruption. Summary table: application comparison. Application key driver for MPLS-TP: benefit over standard IP/MPLS. Carrier core path predictability, easier capacity management, fixed routes. Mobile backhaul: precise sync/timing, symmetrical delay, no routing induced jitter. Enterprise VPN performance: SLAs, hard bandwidth reservation, deep monitoring. DWDM integration: multi-service support, carries legacy TDM/ATM alongside Ethernet. Critical infra survivability: 50 milliseconds protection, NMS managed security.